Okay, so yeah, so yeah, so last time I was telling about Byzantinization, and it was a correspondence between two fermions, with the following OP. Psi of Z, psi star of Z was 1 over Z minus W, and they were related to one boson. Uh, so, um, so this complex fermions can be related to boson by the formula ID phi equals to psi star of psi star psi, normally ordered. And if you want the inverse map, we should write the formulas like psi of z is e to the I psi star of z equals to e to the I phi, psi of z equals e to minus I phi. And if you write these formulas in terms of modes explicitly, then this psi star of z is a sum of minus, well, for negative ends, n over n zn, sum of over positive ends e to the q shift operator z to a 0. And for psi of z, the same formula was e to the plus, e to the plus, e to minus q, z to minus a0. So so we have something of this kind. But, now the first natural thing to do is to try to generalize this to many fermions. So it is of single component fermions. I can consider also multi-component fermions. And it is also natural to try to describe them in terms of free boson. But what are their OPs? So psi psi star of we will now have some index alpha. So the OPs should be psi star alpha of z, psi beta of w equals to delta alpha beta over z minus w, which is equivalent to the anti-commutation relation between their modes, like psi alpha p, psi star alpha p, psi beta q equals to delta alpha beta delta p plus q 0. So if you try to write the formulas like this, we will have a problem because because such formulas for different alpha and beta will now commute, not anti-commute. And this problem is well known, so and to fix it, people use so-called Jordan-Wigner transformation. Well, the transformation looks like this. Psi star of psi star alpha of z should equal to e to minus a alpha n over n zn for negative or for positive. These factors and also some sign factor which is minus 1 to sum over alpha prime sum over, or maybe let us call it gamma, from 1 to alpha minus 1 times a alpha 0. So and the same formula for psi alpha. It is analogous. And this fixes commutation relations, since it turns commutation of different modes to the anti-commutation, because you can imagine this like this. So there is some operator which where oh, a gamma 0. And here we have Q alpha and A alpha 0. So the basic thing is that operator E to Q alpha minus 1 to sum this gamma from 1 to alpha minus 1 A alpha 0. It anti-commutes with such operator for a different number. Goes to 0 when alpha is different from beta. So pictorially it can be written like this. So there is some tail going from 1 to alpha, and there is some tail going from beta from beta to 1. And elements of this tail anti-commute with this charge shift operator. So either the tail of beta meets on the tail of alpha, or the tail of alpha meets the tail of beta. So, and so the point is clear. So the point is that we can write such expressions for the multi-component fermions that satisfy anti-commutation relations between themselves, but they are realized as operators acting on a bosonic Fock space. So. Right. So, all this bosonization, we will remember this because we can use it later. Now, let us think about algebras which can be constructed from these fermions. So, one such example is so we can construct a fine GLN on level 1. So to do this, we introduce generators J alpha beta of Z is a normal product of psi star alpha of Z, psi beta of W, or psi beta of Z. Or maybe we can just say that it is a usual it's a usual normally ordered product from the fermions. And if you now compute OP of this J alpha beta of Z with J gamma delta of W, we'll get what? We'll get the most singular term, which is delta alpha delta delta beta gamma over Z minus W squared plus less singular one. It will be delta beta gamma times G alpha delta of W plus delta alpha delta J gamma beta. So if we say that that these indices alpha beta gamma delta are some, let us denote alpha beta equals to A, gamma delta equals to B. There are some Lie-algebra indices, gamma delta equals to B. Then this OP tells us that G A of Z, G B of W equals to some G A B over Z minus W squared plus F ABC G C of W over Z minus W. And if we write this in components, then it will give commutation relations like J A N J B M equals to N delta N plus M 0 JB plus f abc j c n plus m. And this is a commutation relation for GL and hat. In principle, we could have here some level k, but this is for level k equals to 1. So this central extension equals to 1. And we can also notice that this JAB consists of operators which have dimension 1, because it is 1/2 plus 1/2. So delta of J of beta So, and since the dimension equals to 1, we can consider scaling currents. It makes sense to consider such operators Q alpha beta, which are integrals of J alpha beta of Z dz. So they are kind of related to J alpha beta 0. So there is this big fine Lie algebra, and there is some subalgebra on zeros level, which is just GLN.
What is the thing after, like in the commutator, after the equality, there is an age?
N.
Okay. And the other question is, GAB is symmetric.
Yes, of course.
So when we take the commutator line, it doesn't disappear.
Oh, what do you mean? So this one is antisymmetric. So n equals to minus m. So if we exchange them.
Look at the right one, like the one with the coordinates in like if I it's below, yes, if I take the commutator of that on the left hand side.
No, but to take commutator, you need to you need to place one inside, one outside, compute this integral, compute residue, and so on. So
Yes, but and in the first term is I mean is everything is symmetric.
and the left hand side is symmetric. These are bosonic operators. When you exchange them, so you may write this equivalent that like G B of W G J A of Z equals to G A B over Z minus W W squared plus F A B C G C of W over Z minus W. It's really the same. I've just changed the order of fields, but it does not affect OP. They will be aligned by the radial order in any case. And now let us exchange A and B and Z and W. So here let us Z to exchange Z and W, A and B. So it is G A of Z, G B of W equals to G B A over Z minus W squared plus F B A C of W over, let us change sign here, it will be, oh, maybe we'll sign it like this, W minus Z. We can also write here W minus Z. So comparing this and this, we conclude that GBA equals to GAB, FCAB equals to minus FCBA. Does that answer your question or not? So, is it fine or there are other questions? We see that there is some GLN algebra in this fermions, and actually we can generate GLN group from it, and so there is a obvious action of this GLN on the fermions. GLN acts on this psi alpha stars and psi alpha, and this action is psi alpha goes to some of G, psi alpha star goes to some G alpha beta psi star beta, and psi alpha goes to G inverse of beta, maybe beta alpha, psi alpha. So there is this action which can be obtained from the exponentiation of this one, and it of course preserves this algebra. So we can see this from the we can check the action of this generators on other G's, because a commutator of J alpha beta 0 on so we should write the OP of this J alpha beta with psi, so with psi star J alpha beta of C with psi star gamma of W is what? It is delta, maybe with this psi star. It is delta beta gamma psi star alpha over Z minus W. So if we now try to compute commutator of J alpha beta 0 with psi star gamma of W, it will be the integral around W of this OP, delta beta gamma psi star alpha over z minus W. So it will be delta beta gamma psi star alpha of W. So it means that commutators of these generators act as Gaussian matrices in the fundamental representation. So it's fundamental representation. Now we can ask the following when we are this action. We can ask who is invariant under the action of this JLM, or in other words, who commutes with this J alpha beta 0. We know by construction that if something commutes with them, then this object form closed algebra, because if some field commutes, then if some fields commute, then their OP will also commute. It will also be invariant. So we can easily see that since this this JLN acts on psi's and psi stars as on fundamental and anti-fundamental representations, that by some theorem from invariant theory, we can conclude that all operators should have equal number of psi's and psi stars, and their indices should be contracted. So we should have some derivatives like so answer is
why you say that's the fundamental representation of the
because what happens when we act with a matrix E alpha beta acting on E gamma. If this number of basis vectors different from beta, it will just find 0 in this matrix, or all zeros. But when beta equals to gamma, there is a chance to find 1. And this one will be on position alpha beta. So it is delta beta gamma D alpha.
Okay, but these guys are okay. Right? It's not the output. Okay, it's not the value conversion.
Yes, of course. So So, so it is algebra generated by the objects of this kind. J. So it is psi some case derivative of psi alpha, nth derivatives of psi psi alpha 1, k1, 1, 1, t k2 psi star of alpha 1 dm 2 psi of alpha 2. It is contracted by alpha 1, alpha 2, and so on. Maybe better to say not generated, but spanned by these operators. But if you want to if you want to write generators in a sense such current that all the algebra can be obtained by taking derivatives and taking OPs of them. We see that we can, for example, say that all derivatives can be moved to the first psi by kind of integration by parts, and other terms with non-trivial derivatives on second psi can be obtained by differentiation of these simple operators. So generators of this algebra so we can write that it is something. We can choose different bases in this generators, but we can say that there are some UKs of Z. They are sums of alpha decay psi star of Z psi alpha psi alpha of Z. And this algebra, so if you take this U1 and so on UN and generate from for alpha from 1 to n. If you take this first n generators and generate algebra by them. I don't know how to write this, but well, let it be like this. This algebra is called WN plus Heisenberg algebra with a central charge C equals n minus 1. So if you ask where is Heisenberg, then we can see this first generator. Okay. So U1 of Z is sum from sorry, it is I should have put here k minus 1 in this. So u1 of z is just some psi alpha star psi alpha. Mm. Hmm?
But the number of infinite generators
Hmm.
not include the number of reactors.
Yes, independent generators are first first n.
Okay,
Then
like in principle, I can also take like higher numbers of the reactors.
yes, higher powers of the generators and so on.
But those, I mean, like if I take un plus 1, say, this completely in terms of the other one.
Yes, we can try to see such examples probably. So let me think. So the simplest way to understand that their number is finite is to think about the following. So this fermions can be bosonized in this way. These generators will become some specific functions which are symmetric under the permutation of bosons. So here, let us try to write some formulas for these generators. And if we see that they can be expressed in terms of bosonate, it should become clear that their number is finite, so not bigger than the number of bosons. So. Let us maybe first see it in the example of n equals to 1. So in principle, we have all these generators which are so for n equals to 1, we have uk of z is dk psi star psi. And when I write normal ordering here, I mean fermionic normal ordering. And fermionic normal ordering is corresponds just to taking the regular part. So, but if we try to bosonize them, we should we should not switch to bosonic normal ordering because it will mean that we break this internal structure of psi. We should say that this original normal ordering is this CFT regular product. Psi star of z, psi of z. So it means that we should substitute here these two exponentials, dk e to the dk minus 1, sorry, k minus 1 e to phi of z e to minus I phi of w. Oh, maybe. So the second point should be called w, and first is no, and second is z because we get function at z, and first is w. We should take regular part of this. All this. So we now multiply these exponentials like like bosonic exponentials, and write that it is wk minus 1, 1 over z minus w, w minus z, e to the I5 w minus I5 z. It's normally ordered. And we should take a regular part in this expansion. So to find who is regular, we should expand it as a series in w minus z, and it will give what? It will be sum of so we can just subtract a singular part of this this expression, which corresponds to minus 1 term in this to the first term in this exponential, because the other terms will be regular. So so it will be this is computed at w equals to z. So So we first want to expand this exponential factorial, and then expand what stands in the exponential. Sum over m equals 1 to infinity, 1 over m factorial power L. And here we will get dm phi of z to 2 power L times z minus w to power lm lm minus 1. So and then take z equals to w. We see that these generators will be so we need to take the coefficient when where lm equals to k and multiply by something. So Hmm?
Like all the second sum together.
What do you mean?
Because like when we
Yes, I'm idiot. Actually, we have no, it's 1 over factorial, and we have yeah, we have over sum over different m's, m1 and so on, m1 and so on, ml, m1 factorial, ml factorial, and here we have yes, sorry, m1 and so on, dml phi of z, and here we have sum of mls minus 1, sum of i's. So you see that so is it fine? So we can say that it equals to uh, mm, to k factorial, so it equals to the sum 1 over l factorial, uh, sum over k factorial, m1 factorial, ml factorial, and that sum of mi's equals to k. So to be precise, k minus 1 factorial. And here we will have these powers, like dm1 phi dml phi. So is it okay? But if you look at U1, we see that this U1 is precisely d U1 is precisely d phi. So in this current. So so this U2 and so on. U1, du1, and so on. U3 of uk will be a function of uk is uk of u1, du1, and so on, because u1 is id phi. So is it fine? Not. Hmm? Oh, but this is the separators will not be independent for a bigger case, but nevertheless they are still nice because of the following property. Let us take OP of UK and UM. UK of M of Z, UM of W. So we see that different terms of this sums have a regular P because there are different fermions. They don't interact between each other. So it can be immediately written as a single sum from alpha over alpha. And it will be so we write here dk minus 1 psi of z psi of z d m minus 1 of z psi star of z psi star of w psi of w plus something regular. And we can rewrite this. So now we should compute pairings between this psi's alpha, alpha, alpha. So one term is when we pair this psi with this one and this psi with this one. So it will be d z k minus 1 d z m minus 1 1 over dwm minus 1 1 over z minus w squared. So one term. Another term is when another two terms is when we pair psi with psi star and psi star with psi. So it is z k minus 1 so something of this kind. So we will have something like minus 1 to k minus 1. I think some factorial, probably k plus m minus 1 factorial. I think over c minus w to k plus m. And then we need to expand these terms. So it will be plus minus 1 to k minus 1 1 over z minus w to power k psi star alpha of z Oh, actually, I don't want to write all those terms explicitly, but idea is the following. You see that the only terms which you can get in this OPE are constants and something which is again bilinear in psi, so it has this form like sum from 1 to n psi star alpha, probably some derivative of it, and some other derivative of psi alpha. So it will be some combination of such terms. Psi star alpha of w, maybe d a minus 1, d b minus 1, psi alpha of w. And if you want to transform such a term, plus, if you want to transform such term, we can write that it is d a psi star. Well, let's write like this: d a plus 1 psi star alpha of w psi alpha b minus 1 w. Hmm? Hmm?
So, can you explain how we go from the first line?
I've just written OP of this fields plus something regular. Hmm? So we have two expressions which are quadratic inference, and they have terms where we need to pair this psi with this and this psi with this. It is this term. Then we have a term where only these two fields are paired. It is this term.
Okay.
Yeah, the last one. So I'm saying that we get only such only expressions of such form, and when we expand everything around W, we will have some number of derivatives acting on psi star, and some number of derivatives acting on psi. But we can move derivative from one term to another one by such obvious identity that d a psi star alpha d b minus 1 psi alpha. So if we use such identity multiple times and also to also apply it to this operator, we can move all derivatives to psi star and finally we will see that OP of UK and UM is some combination of 1 over z minus w to power, well, we can find this from a dimensional argument. So we will have some sum of c, k, m, n, u, k of w over z minus w to k plus m minus n. And also derivatives. U k and l d l minus k minus m minus l and dl u u n of w. So the point is that this and here we should also actually write a sum from n from alpha equals to 1 to n. So this term will have power n here. So and this algebra which we obtained here, see that the number of fields appears only in one term. All other commutation relations do not know about the number of fermions. So we can look at this at some algebra relations. And we can call this algebra with such relations W 1 plus infinity algebra. And if you want to get W algebra from this, we need to impose this extra nonlinear conditions. So W 1 plus Wn plus Heisenberg with c equals n minus 1 is this W1 plus infinity factorized by nonlinear relations. So is it fine? And sometimes, if you want with this W algebra with c equals n minus 1, it might be easier to work with this infinite series of generators and do not care about nonlinear relations between them, rather than to write generators of Wn and all these relations. So some statements can be proved using only this representation. So is it? So is it fine? Yes, yes. So, and this W algebra C equals n minus 1 can be obtained by reductions of this W 1 plus infinity. So.
Okay, because now like the generators in W1 plus infinity are not like explicit in terms of like I have just like if I look at the because I mean the stupid way to recover the WM plus Heisenberg is just to settle the terms above a certain number to zero, right?
Yes, we can do this. Like we can say that it is algebra generated by n fermions.
But in principle, like if I have the W1 plus infinity is present in terms of this UK stuff, which are not explicit in terms of the number of terms inside.
Well, in a sense, commutation relations between these UKs almost don't know about the number of fermions. They look universal. So the only place where this n appears is in this term.
But what is the relation between these and the real one? Is there some relation?
So if it is possible to express the generators in terms of generators GLN1, yes, it is possible because mm, here, so this algebra was defined by properties that it should commute with GLN. And we can, of course, find generators which commute with GLN also in this GLN1. For example, we can consider regular products of G alpha beta, G beta alpha. We can consider such Casimirs. Like, mm, what shall I raise?
But like what is that like physical requirement one would start to define and these are the percentage of the terminals of the bosons?
Why this? Why are the algebras interesting for physics? Is this question? Oh, I don't know real physical systems where the W3 appears, but there is some minimal model with some numbers I forgot which precisely, which has W3. Maybe it's something quite exotic. Usually, usually they are interesting because they are related to something by some dualities, like to higher rank Fuchsian systems or to gauge theories with groups bigger than SU2. So. So for me, it's the most natural motivation to find the algebras as counterparts of some natural objects in other theories, because as itself, they don't look very nice. So, but maybe it's just that we don't understand something, because if we talk about Virasoro algebra, there is some geometry behind it. It is some central extension of the algebra of vector fields, and this vector fields correspond to symmetries of a complex structure or to variations of this complex structure. And if we talk about double algebra, it should be related to so-called double geometries, which should somehow generalize complex complex structures on the manifolds, and I don't know what it is. Why is it natural? So people have some ideas what it should be, but I don't know if there is any rich science around this. So.
But these are largely complex structure in which sense?
Mm, so well. Uh, so let me try to say this. So a usual complex structure is something that is some object such that its deformations are described by Beltrami differentials, which are 1 minus 1 forms, and probably higher complex structure should be something which is deformed by n minus 1 form. Yeah, so I was telling that there should be some other deformations. So, for example, the dual space deformations of the complex structures in the space of quadratic differentials. So probably it should be correct. And here there should be some deformations, so that dual space to this is some 3 differentials, 4 differentials, and so on. And I don't know what is the geometrical meaning of this, although people study such questions. So, so other questions? Yes. So. I also want to tell that we can combine such constructions with Bosonization. So, for example, so maybe I will erase this. So for example, we can take this construction of GLN hat at level 1 and bosonize it. So J alpha beta from for alpha different from beta can be written. So I will not write this in full details, but if you take that fermionic formulas and write symbolically that it is I of e to the I of phi alpha, it will become I phi alpha minus phi beta. It's for the off-diagonal elements. And if you write it for diagonal elements, then So J alpha alpha of Z of Z. We should take a regular part of the expression I phi alpha of Z e to minus I phi alpha of Z. So it means that we should take the exponentials together, like e to I phi alpha of W minus I phi alpha of Z over Z minus W, and W minus Z regular. And so first term is pole, and second term is derivative. So it is I d phi alpha of W of Z. So there is such representation. And for example, let us look what it gives for GL2. GL2 on the level 1. So in this case, we will have a generator E, which is so J12 will equal to E to the I phi 1 minus phi 2. And the same for G21, the opposite exponential. And there will also be J11. Maybe it's better to say that there is there is J11 which is ID phi 1, and the J22 which is ID phi 2. And if you now want to turn this to, well, if you want to write this algebra as SO2 plus Heisenberg, we can do the following change of variables. We can say that
what you meant, like, was like the first term that you think you need to implement the identity.
No, because it is a regular product of two fields. So it means by definition. So when we write A of Z, B of W with this B of Z with these brackets, it means by the definition AB 0 of Z. And who is AB0? It is the following. We take OP of A of W B of Z and say that it is a sum from K equals to minus infinity to N AB K over Z minus W to power K, ABK of Z. So we have some number of singular terms divided by Z minus W to some power, and we should drop all of them. And W minus Z to the power K, sorry. So we write this OP, we remove all singular terms and take a term which has a defined limit when W goes to Z, which is a
plus delta A.
so
The power of the denominator, is it there plus K plus the dimension of the
no, because so of course it depends on the mutual structure of this product A times B. Like we can have fields with mm, we can have OPs with non-integer powers of W minus Z. And in this case, this regular product will not make sense. But if this series is in integer powers of W minus Z, then we can define the regular product. And so delta of a B, so delta of this operator AB equals to delta of A plus delta of B by definition. Because in general, when we consider some OP, like A of W, B of Z, it is a sum of Z minus W to what power? Delta C minus delta A minus delta B. Maybe. Yes, times some operators C of W. C of W. Right? So if you take a term with power 0 in this expansion, it means that a dimension of this term is the sum of dimensions of A and B. Sorry.
So if we define also the non-diagonal term in the same way.
But non-diagonal OP for non-diagonal terms is already regular, so we can just multiply this exponentials. We don't need to compute anything.
But still you need to normal order.
Yes, they are normally ordered.
Yeah. So
Each of them was normally ordered from the beginning. And if we multiply exponentials that almost commute, we don't need to order anything.
no, but what I'm saying is, I don't know, like if I take JAA, okay, to be the normal order of the exponential of the derivative of phi, for example.
How can you do this? So what is exponential of derivative of phi? Something very irregular. Hmm? But why should it have any relation to this fine Jelen algebra?
I don't know, like what is the structure behind what I'm saying is like seems to me like more similar to the construction of the non-diagonal term. This to me seems more a construction to obtain what is the algebraic structure that you want.
Oh, but wait, we don't have any freedom here. We constructed this GLN algebra define J-line algebra from the free fermions, and this construction can be written only in terms of CFT. So this can be equivalently written that it is a regular product of psi star alpha of the psi beta of z, in a sense that we should take two fermions, put it at z and at w, then send z to w and take a regular term of the OPE. We were just lucky that this equals to fermionic normal order. So, because we know, thanks to the Wick theorem, that OP of psi star, maybe I can write it here. OP of psi star alpha of z, psi beta of w is delta alpha beta over z minus w plus normal order of psi star alpha of z, psi beta of w. It is thanks to the simple fermionic anti-commutation relations, we can write this identity. And then, if we want to compute regular product between different fermions, like alpha is different from beta, we can just multiply them. There are no singular terms, so we can put z equals to w immediately. But if we compute this for alpha for beta equals to alpha, this prescription says that whatever realization of these fermions we use, whatever is going on, we should take OP of these two fields at z equals to w, remove this first singularity, which is 1 over z minus w, and then send z to w in the remaining term. And this is precisely what we are doing here. So, right, that this exponential equals to, so let me write it somewhere here. So we say that e to I phi alpha of z, e to minus I phi alpha of w, they are normally ordered. So it equals to e to the I phi alpha of z minus phi alpha of w, normally ordered. So, over z minus w. And then we expand this exponential. So it is, so we expand what is in the exponential. It is e to I z minus w d phi alpha plus I over 2 z minus w squared t2 phi alpha plus so it equals to 1 over z minus w plus I d phi alpha. Well, we don't need normal order in here because it is just one field. Plus, plus something of order z minus w. And we now compare this formula with this one. and see that and with this one. So we see that uh, this regular product. So what we are computing here is the regular product of psi star alpha, psi alpha of W. No, well, so so, so this is psi star of Z, psi alpha of W. So it means that psi star alpha of Z of W, psi alpha of W, regular product equals to I d phi alpha. It's actually the same relation which we obtained for Bosonization of a single terminal. This relation between psi star psi and bosonic current I d phi. So is it clear or not? Mhm. So okay, but I want to do the following. Let me arrange this. So let us take this GL2 and say that this phi 1 equals to phi plus phi minus over 2, and phi 2 equals to square root of 2, and phi 2 equals to phi plus minus phi minus over square root of 2. So OPs of phi plus. I don't know what are the OPs of phi plus and phi minus. So it's 45 degrees rotation. So they should be the same, right? So and if we introduce this change of variables, then we see that J12 equals to e to I phi minus I square root of 2 phi minus J21 is e to minus I square root of 2 phi minus J11 minus J21 equals to I square root of 2 phi, d phi minus. So this is SL2 hat the level 1. And J11 plus J22 equals to I square root of 2 d phi plus. And this is Heisenberg. Maybe we can write it as GL1 on the level 1. So probably those who went to Misha's talk probably don't remember if everyone were there. You might have seen this formulas for bosonization of SO2 hat to L1. So it, it is almost like for the fermions, but here dimensions of this exponent is 1, and for the fermions it was 1/2. So here we have square roots of 2, so it's SO2 1 and not fermions. Yeah. So let us go further. So this was so. So these are algebras of bosonic nature, but we can also try to construct something involving fermionic generators. Namely, let us try to construct some superconformal algebras. Maybe start from there. Namely, let us take three fermions, psi1, psi2, psi3. Such that their real fermions, psi of z, psi j of w, will equal to delta ij over z minus w. And just multiply them. Multiply all three of them. So let us say that there is a operator g of z which equals to psi1 of z, psi2 of z, psi3 of z. And try to consider the OP of G with itself. So this is an operator of dimension 3 over 2. So let us write all possible pairings between these psi's. So we have so if we pair only two psi's, we will have what psi2 of z, psi 3 of z, psi 2 of w, psi 3 of w, plus permutation. And these terms actually vanish because we need to because we are interested only in the singular part, and the singular part appears when we put z equals to w. But there are two fields of the same. There are two fields of similar kind, like psi2 and psi3, and if we multiply them, it will just give 0. So we should this will be regular. Uh, so we need to go further and consider a pairing of two such fields. Uh, mm, mm, hmm?
They vanish because they are all dealt with the same contribution but different signs due to the fermionic star.
No, because we have psi2 squared. So psi2 of z, psi2 of w equals to it equals psi2 of w squared, which is 0, plus z minus w d psi psi of w, d psi of w, psi of w.
Why can't they do DOP?
You can, and you will get a regular expression because psi.
Isn't something that causes one over?
No. It is already the result of OP. This is normally ordered. And then we should see what happens under this normal ordering. This is the term where we paired only one fermion in each of this products. So.
So we use anti-commutation relation to move the two and the three. Right?
Yeah, we exchange them.
Take a sign and then we do this that we were saying.
Yes. So it means that we need to take another pairing. Here distance between these fermions is 1, so and there will be minus sign, minus 1 over z minus w squared, and here we will see psi 2 of so we pair, for example, psi2 with psi2, and we will have psi 3 of z, psi 3 of w, plus other two terms. And now we do precisely this. We expand psi of z around psi of w. So it will give us psi 3 of w d. So yeah, d psi 3 of w, and maybe plus psi 2 of w d, psi 2 of w, plus psi 1 of w d psi 1 of w. And so we think about the sign, if it is correct or not. Probably it is correct. So I forgot which sign we should have here, but probably. in Brown, but it seems that it should equal to well, we can also add some I factors. It does not matter, but we now can recognize here the energy momentum tensor of the fermions, and this energy momentum tensor. So it was minus 1/2 d psi times psi. So it is minus 2 T of W, and it is also divided by and wait, sorry, I forgot another term here. Of course, there is a term when we pair everything, psi1, psi2, and psi3, and this term comes with a coefficient so minus, probably minus 3 over W minus or Z minus W squared. Sorry, I forgot this. So it equals to minus 3 over Z minus W squared plus this divided by Z minus W. So we see minus 3 over Z minus W squared plus 2t. I should have looked at the relations actually, but maybe let us write it like this: minus 1/2, and then let us write it minus 2, then there will be 3/2 plus t. So we see that there is this odd operator with dimension 3/2, and OP of this operator with itself gives gives an energy momentum tensor plus some constant. So it means that there are some generators like well, I'm not sure about all these coefficients. So there is a relation like GP with GQ and a commutator equals to 3/2 delta P plus Q half P delta P plus Q plus L P plus Q. And so in principle, I think so. Here, central charge equals to well, there should be a little bit renormalized. So central charge here is 3/2 because it is 3 real fermions. And I think in the general case we should put here C instead of 3/2. Because, for example, if we take more fermions and add the same term here, it will double the central charge. So it at least it behaves in the same way, and so it is actually C. And this is called, if I remember correctly, an SR algebra. And here is one tricky point that in principle fermions can have either integer or half integer numbers. So usual fermions, like normal fermions, have expansion in the integer powers of z, in sense. So let me write it here. So if you have algebra like psi p with psi q equals to delta p plus q 0, then one possible option is p and q are in 1/2 plus z. So in this case, psi of z is sum of psi of p, or z p plus 1/2. So it is in Laurent, in the space of Laurent series. But we can also say that these p's and q's are integer. These are called NS fermions, but there is also Ramon's sector where p and q are integer. This is psi of z, which is sum over integer numbers. It is in the square root of z, c of z inverse. So of course, if you take one of these fermions to be in the Ramond sector, we will have one of these fermions. Well, if all these fermions are Ramond fermions, then this will have integer indices, but if one of them is NS, then they will be half integers. Or if all three of them are in the NS sector, then we'll have the same. And the tricky point about this Ramond sector is the following. So imagine that we want to compute expectation value of the energy momentum transfer. So we want to compute this. And it is the expectation value of so 1/2 psi of z, this regular product, d psi of z. But let us see what happens when we compute this for Ramond sector and for Neveu-Schwarz sector. So for NS, this correlator psi of z psi of w equals to 1 or z minus w. So a correlator of psi of z d psi of z psi of w. Oh, sorry, d psi should be on the first one. D psi of z psi of w is is 1 over z minus w squared, and there is no regular part. So if you remove singular part, then we remove everything. So in this case it is 0. But let us try to, oh sorry, psi of w, but ns. But let us try to do the same computation for Ramond sector. So so first let us compute the correlator in the Ramond sector. So here we will have psi p over z to p plus 1/2 sum of psi q over z to q plus 1/2 0. And what we have here, we have the difference in the is integer, q is integer. So the difference of the Ramond sector is that we have zero mode, and for this zero mode we have psi 0 squared, 2 psi 0 squared equals to 1, which means that psi 0 squared is 1 over, so psi 0 squared is 1/2. So so we have one term of this kind, w, which is 1 over square root of cw. And we also have 1 over square root of zw. Sum from 1 to infinity. So this q should be negative, and this p should be positive. So it is w over z to power p. Oh, it is 1/2. This expression then and this is I think it is 1 over z over w minus 1. So it can be written as so we can collect these terms together, and it will give 1/2 1 over square root of WZ, and here it is 0 over W minus 1, and here it is 0 over W plus 1. So in total it is 1/2 square root of 0 over W plus square root of W over Z over Z minus W. And we want to expand this expression around Z equals to W. Because so we want to look at the first, so we want to look at the linear term in Z minus W. So to do this, we expand so maybe it is a bit boring. So probably I should write somewhere here that s square root of Z equals to square root of W plus 1 over 2 square root of W Z minus W plus minus minus 1 over 8 probably. So we need this two integral expansions, and we see that these terms no, let us see. Yeah, yes, and these terms will cancel, and the only term that remains, the only terms that remain are this one and this one. So we will get here. So signs probably are correct. So we'll get here 2 plus 3 over 8 minus 1 over 8. Yeah, so plus something else. So we get here 1 over z minus w, it should be a plus. So what is it? It is 1 over. It is 1 over 8. 1 over 8 z minus w 1 over w squared plus sum all of z minus w cubed. So and now let us look at this term. It says that expectation value of the energy momentum tensor in this Ramond sector is equal to 1/2 of this deep psi of z psi of z. So we should take we should differentiate this in z and divide by 2. So it equals to 1 over 16 w O plus t of w expanded around w. So it is 1 over 16 w squared. So it means that if we take this fermions in the Ramond sector, we will get some state with dimension 1 over 16. So this Ramond vacuum has dimension 1 over 16. And this happens in CFT with C equals 1/2. So actually, this state corresponds to spin operator in 2D Ising model. It has conformal dimension 1 over 16. So, and also here, if you take Ramond, if you take Neville-Schwarz operators, then this Rosser vacuum will be just a vacuum. But if we take something from the Ramond sector, then this vacuum state will have a non-trivial dimension.
How do you read the dimension 1 over 16?
Because expectation value, so delta of sum of ln over wn plus 2 delta equals to delta L0 over w squared delta.
So you're saying that the vacuum of the Ramond sector is dimension 1 over 16.
Mm-hmm.
And there is some operator that, okay, but so there is an operator that generates it from the NS vacuum.
Yes, we can introduce this operator. So we should, well, NS vacuum is the real vacuum of our theory, which corresponds to identity operator. And if we consider a fusion of any operator with identity operator, we will get this operator. So.
But is it like, is it something related to like high temperature, low temperature, one easing, or the two sectors are the high and low temperature sector of easing?
No, it's different. So this Eisen is in the critical point because it's CFT, and there are actually two operators here with dimension 1 over 16, as in the Eisen model. There is this sigma operator, and there is a disorder operator, which is non-local. And if you consider both of them, then mm, mm, OP is like OP of sigma with mu is OP of psi with sigma is mu. OP of psi with mu is sigma. It should be in the Eisen model.
No, okay, but okay. So the easy model is R states basically.
No. Right. There are other fields like there are these fermions. If you multiply homomorphic and anti-homomorphic fermion, it will be the energy operator. Mm,
Now,
so
like, what I'm not understanding is this. So if I have easy here, easy model CFT is represented by this R sector.
no. There are different states in in Ising. For example, there is, of course, a vacuum state corresponding to trivial operator to 1. There is a state corresponding to NS vacuum with perturbation like psi minus 1/2, psi bar minus 1/2. Yeah, it corresponds to the energy operator. So it's clear that they live. So this operator and identity operator live in the same fermionic module, but it is clear that Versor generators are quadratic in fermions, so they cannot change this parity. So this operator belongs to different Versor module. On this module related to this operator and it corresponds to energy, and there is a vacuum representation which corresponds to trivial operator. But this is an S vacuum. But we can also consider this R vacuum, and we can say so probably so. I think R vacuum corresponds to sigma, and also we have this zero modes, if we put precisely. So when we consider fusion of a fermion with this vacuum, then psi zero vacuum should correspond to mu because of that OP. And psi zero bar should act by 1, I think. We can impose such extra condition. Because otherwise there will be too many fields.
So there is like some duality that maps one sector to the other.
what do I mean by sector?
What do you call it? Like there is a way to map the vacuum of the vacuum and the NS vacuum.
Oh, but what do I mean by a map? If
Like there is like the vacuum of NS is like the vacuum at low temperature of the at the vacuum at high temperature of easing model, and the other is the vacuum of easing at low temperature. Because like the disorder order operator is like it's like performing the duality between high and low energy of like high and low temperature of easing.
mm,
There is that makes sense.
no, no, the actual vacuum of theory is uh, an S vacuum. In a sense, it should be some state with the lowest lowest dimension. And then
Well, but wouldn't be like the minimizer of the
hmm?
substance. Like it's not the minimizer of the substance.
No, why?
Because like at high temperature,
But we are in CFT, so
yes,
it
but
is
that
critical
temperature is
temperature.
the model the quantum model 1+1.
Mm-hmm.
It's like there is I don't know there is this duality between like the state that is order at low temperatures
Yes.
and then and in which like you have an expectation value of the order parameter.
Mm-hmm.
And then there is the stuff at high temperature, or whatever you want to call it, in which the system is disordered. And then there is
Mm-hmm.
like the disorder operator, which is your order parameter.
Yes, but it is a question. So I don't remember this precisely. Um, mm.
If you want like this, here is describing like the transition between these two phases, like the high and the low temperature.
Yes, but
And
I think.
the,
But in safety, this is the difference between the sectors is the action of if you want to map a state which corresponds to mu to state which corresponds to sigma, we just need to act with sigma zero with psi zero. It is there is an OP that sigma. Oh, maybe I can erase this. So OP that comes from the latest construction is psi sigma is mu, psi mu is sigma. follows from the latest construction of this fields. Then sigma corresponds to Raman vacuum. And let us try to use this OP. So sum of psi p over z to p plus 1/2 acting on a vacuum, Raman vacuum, equals to 1 over square root of z psi 0 Raman vacuum plus something else, plus descendants, and so we can hear it as natural to say that this corresponds to mu. And if we do this again, like say p over z, p plus 1/2 Raman vacuum psi 0, it equals to 1 over square root of z Raman vacuum. So and this is and this is mu, and this is sigma. So it has nothing to do with change in Raman to Navier-Schwarz and vice versa. It is a multiplication by zero mod of a fermion. I don't know. One of the possible options is to study this lattice Eisen model and its explicit relation to CFT. You know, is it interesting or not, or is it too technical? Hmm? Instance not very interesting. Well, so maybe then I can tell something about relation to azimuthal deformations like of CFT. Would it be interesting? No. So, are there any other questions about today? Okay. Here we can also try to do the same for, I think, complex fermions and get n equals to superconformal algebra, which will also contain fermionic current, but maybe it's not much. Okay, thanks for your attention. So see you maybe next Tuesday. Okay.